Welcome everyone to the seminar. The lecturer today is Erman, and he will speak on boundedness questions for polynomials in many variables.
Great, thank you.
Just the rest of us mute ourselves. Yeah, good. Daniel, take it away.
Yeah, thank you. So thank you so much for the invitation, and also for putting this together. It's been a really great event, and I'm pleased to be part of it, and I'm just really pleased it's happening. I also want to start with a bit of an unusual comment, which is I know that this is just a difficult time for people in many different ways, and I hope I can just say hello and seeing all these names of friends, this incredible list of names of friends and participants makes me think about many of you and hope that we can do this in person soon enough. I'll add one more comment, which is for this seminar in particular, this fellowship seminar is a place where I learned a great deal of math, and I met many of the people here in the audience and many of the people whose work I'll be citing today. So it's a particular pleasure to be speaking here. Yeah, all right. So anyways, that's that. Let me get started. I'm going to share slides, which is going to make David go nuts, but I thought this would be the best way to do this. I will say, in my limited experience with these Zoom talks, my sense is it's essential to get lots of questions. So I'm going to try to go slow. I'm going to stop for questions a lot. I know it's hard it can be hard to ask questions because you don't have the visual cues you would have in a room. But please, I really want to encourage lots of questions. I think that's really crucial, and I want to take as much time as possible answering questions, going off on tangents, things like that. That's where I think the most interesting stuff will be.
And it's best to put the questions in the chat box. If you spread them between chat and questions, it's hard to keep track of. So we'll watch the chat box and interrupt Daniel when there are questions.
Yes, please interrupt. I don't have the chat box up at all. So please interrupt the host when there are questions. All right. So let me get started. I'm going to talk about questions about polynomials in many variables. And a lot of this will not be my own work. A lot of it will cite work of others, some of whom are in attendance or are part of this seminar. But the original work that I reference will be joint with Stephen Sam and Andrew Snowden. Okay. So I'll get started by talking about Hilbert's results. So let's go way back. K will be a field throughout. S will be a polynomial ring in n variables. And I don't want to repeat this. So ideals and modules and so on will be homogeneous throughout. So the variables all have degree 1. And when I talk about an ideal, I'll always mean a homogeneous ideal, or modules will mean homogeneous, graded modules, things like this. I just don't want to constantly be repeating it. So there are two very famous theorems of Hilbert I'll start with. One is the Hilbert basis theorem, which says that the polynomial ring over a field is Noetherian. Right? And being specific, it means every ideal in the polynomial ring is finitely generated. And then there's the Syzygy theorem, which I'll cover a little more on the next slide, but it says that every module has a free resolution that ends after n steps. And by combining these two theorems, you can get a huge array of finiteness results in modern algebra. I mean, it's kind of, I think, a hallmark of algebra is that we expect boundedness results or finiteness results. So just for example, if you have a family of ideals, if you're studying some reasonable family of ideals, we would expect that to have only finitely many different Hilbert polynomials arise in that family. Or if you're interested in Betti tables, there'd only be finitely many different Betti tables that could arise. Or you might have a family of ideals and ask about the primary decomposition, and we expect that finitely many that there'd be a maximal number of associated primes for ideals in some sort of family. And these sorts of results, at the end, they show up throughout algebra, throughout algebraic geometry, and they just very often reduce to these kind of essential Noetherianity pieces, that parameter spaces are Noetherian and things of this vein. So this finiteness is really fundamental to the study of the polynomial ring and things related to it. But the launching off point for me today, or for this talk, is going to be a kind of silly comment, which is both of those theorems seem to fail as n goes to infinity. I mean, they're not uniform in n. So like the Syzygy theorem in particular, the bound depends on the number of variables. If n goes to infinity, then there's no bound. And so the overarching question I want to start with for today is, are there interesting analogs of these results as n goes to infinity? And the answer is yes, and we'll get to those as we go forward, but that's kind of the opening bit. All right. So let me talk about projective dimension and the Hilbert-Syzygy theorem in a little bit more detail. So we won't need a ton about this, but I'll cover a little. So if you have an S module, then you can always build a free resolution of that module. And by a free resolution, what I mean is it's a complex where each Fi is a free module. I wanted to resolve the module M, so I want the co-kernel of this first map to be M, so that we get, it's resolving M. And then I also want it to be exact, other than it's that zeroth co-kernel being M. I want it to be exact from there on out. So after that, I want the image to equal the kernel at all the other places. So it's a complex which is exact everywhere except for at the very end, and at the very end, the homology is the module M. And that's what we mean by a free resolution. We're in the graded, for graded modules, you can do a little better if you wanted. You could talk about minimal free resolutions, but I won't actually need that for the things I'm going to say today. All right. So then the projective dimension of M, which will denote pdim, is just the minimal length of free resolution of a module. And this makes sense not just over the polynomial ring, it makes sense over any ring. You can have can ask about the minimal length of a free resolution. We'll set the pdim to be infinity if there's no finite resolutions, no finite free resolutions. And I want us to think about this, if you haven't studied this before, I want us to think about this as a measure of the complexity of the module. So free modules are, I think, reasonably understood to be the simplest modules. Free modules are essentially like vector spaces. They have bases, there's no relations, they're fairly easy to understand. And a free resolution is like an attempt to compare an arbitrary module to a free module. You approximate it by one free module, and then you take the kernel. And then you approximate that kernel by another free module, and so on. And so you're, instead of studying a single module, which is can be a complicated object, you can study it by comparing it with free modules. So you replace a single module by this big family of free modules, and there can often be an advantage to studying something in that way. So I sometimes think of it the way you might study a manifold by comparing it to simplices. You find a triangulation and a simple cover of it, or even a little bit the way you might study a function by comparing it to polynomials through Taylor approximations. The process of turning, studying a module by comparing it to free modules is somehow similar. And the projective dimension is a measure of how deep you need to go in studying the module. So the Hilbert-Syzygy theorem says that there's a global bound on projective dimension. So if you're doing the, remember S here is the polynomial ring in n variables. And the theorem says not only are these free resolutions always going to be finite, in fact, there's a uniform bound. It's the projective dimension is at most n, and that's independent of the module. It's a global bound. All right. Now, just for one kind of silly example, if f is a non-zero polynomial, then you could take your module to be the quotient, s modulo the polynomial, and then you can find a free resolution. That's just, you know, s maps to s by the map f, by multiplication by f. And so the projective dimension is 1. And I want to flag this example, not just for someone who's never seen a free resolution, so you see one kind of silly one. I want to flag it also to point out that Hilbert's Syzygy theorem is very often not sharp. So if I'm in a polynomial ring in 10 billion variables, but I'm only studying s modulo a single polynomial, then the projective dimension is 1, whereas Hilbert's bound would have been the number of variables, 10 billion. So it's a uniform bound, but it's often very far from accurate in any given example. All right, let me pause a second. I was trying to target the beginning at first year for people who had taken a first-year graduate algebra course. So maybe let me pause for those folks in the audience. If there are any questions so far about projective dimension or Hilbert's theorems or my setup, that would be a good time for someone to ask in that vein. All right, I'm going to move on. Please jump in at any point. So we want to ask what happens to Hilbert's theorem as n goes to infinity. And the first pass is, well, nothing good seems to happen, right? So as n goes to infinity, there's one natural limit of the polynomial ring in n variables, which is you just take the polynomial ring in a countable set of variables. And for this ring, the basis theorem fails. You can find an ideal with an infinite that requires an infinite number of generators. And the Syzygy theorem fails. You can find ideals that have higher and higher projective dimension. So for instance, if you take r variables, the projective dimension is r minus 1 of that ideal. Or if you took, the infinitely many variables, then the projective dimension would be infinity. So both the basis theorem and the Syzygy theorem at first pass seem to fail in infinite many variables. So if we want analogs, we've got to look closer and kind of narrow what we mean. So I want to narrow the question a bit and drill in on just kind of one somewhat silly seeming example, but I hope it'll clarify the ideas. So imagine that we were studying an ideal generated by 5 cubic polynomials. And I'll pause here to note there is nothing special about 5 or cubic. I'm just choosing some fixed number of polynomials and some fixed degrees. All right. But imagine I'm studying an ideal generated by 5 cubic polynomials in 10 to the 10 variables. Okay, so there's just an enormous number of variables, but a very small number of generators for your ideal. Hilbert's Syzygy theorem would tell us that the projective dimension is at most 10 to the 10. But I suspect, even if you haven't studied this before, things of this vein, you might have the intuition that that's absurd, that for 5 cubic polynomials, there's no way the free resolution could go on for billions of steps. There must be a way to do better. And so that's maybe an intuition. We'll start sharpening that with Stillman's conjecture on the next slide. So what I want to do, even though these naive generalizations of the Hilbert basis theorem and Hilbert Syzygy theorem fail when you go to an infinite number of variables, I want to note, I'm going to show today that there are some frameworks where there are analogs of those results, but you need to get the kind of framework correct in order to see it. All right, so let's move to Stillman's conjecture. So I'll spend a bit of time on this slide, and this is an essential one because we'll come to it a lot. So Stillman's conjecture is a generalization of this question I asked on the previous slide. So I want to study, are polynomials of degree at most d? So like on the previous slide, it was 5 cubic polynomials, but now we'll take r and d. And the question is, can you bound the projective dimension of such an ideal solely in terms of r and d? In other words, without using Hilbert's bound, without referencing the number of variables you're working with. All right. So to be concrete, if I have an ideal of 5 cubic polynomials, can I bound the projective dimension of that ideal solely in terms of the 5, the number of polynomials, and the 3, the degree of those polynomials? And it's worth just mapping out. If you haven't thought about projective dimension before, it's easy to underestimate how complicated it is. So first of all, any such bound would have to involve R. That's fairly easy to see. If you look at the projective dimension of R linear forms, I guess it's R minus 1, then that grows with R. So even just for linear forms, the bound would have to involve R. A little more surprising, at least to me, when I was in grad school, I remember being shocked by this, that you can find ideals generated by 3 polynomials of arbitrarily large projective dimension. So that result was proven by Bruns, but then there's this other theorem of this list of authors who sharpened it, and they showed that in fact for any degree d, you can find 3 polynomials, f1, f2, f3, of that degree whose projective dimension grows via this horrible doubly exponential kind of thing. So if you want to bound the projective dimension of an ideal of r variables, you're going to need to take into account the degrees of if you want to bound the projective dimension of an ideal of r polynomials, that bound will necessarily involve the degree of the polynomials as well. All right. So Stillman had asked whether such a bound existed. And I think Mike is here, but if not, maybe I misread, but maybe you can correct me. I think he told me at one point, and if I get this wrong, Mike, please correct me. I think he told me that originally this came about by conversations thinking about an alternate way to compute Grosvenor bases, that there would be, if you could get a bound on the projective dimension and the regularity of an ideal, then you could use linear algebra techniques to compute Grosvenor bases a different way. And so the question kind of arose in that setting. Was there a way to bound the projective dimension solely in terms of the degree and the number of polynomials? I may be misremembering that, but please correct me if I'm wrong, Mike. Okay, but so this was a conjecture. It was open for maybe, I didn't write down the year in front of me, but around 20 years, I think. And then it was proven by Inanion and Hockster. And I'll go through some of the ideas in their proof soon. But I want to claim, before we go on, that this is a version of Hilbert's Syzygy theorem as n goes to infinity. It's saying that while we can't uniformly bound all modules or all ideals, we can't bound the projective dimension of all ideals simultaneously as n goes to infinity. We can do so if we incorporate some numerical information about the ideal. Is there a question?
Yeah, someone is asking if you can produce such examples with 2 generators.
What a great question. No. So it turns out with 1 generator, the projective dimension is always at most 1. And with 2 generators, it's always at most 2. So that pattern really breaks poorly when you get to 3. So with 2 generators, There are only, the free resolution basically depends upon whether they have a common factor or not. So there's only really two cases, the case where there's no common factor, and then the case where there is, and those are both easy to analyze. And then somewhat bizarrely, when you get to 3 generators, it's total mayhem, and things really get wild. Yeah, it's a great question. Other questions? So again, I want to think of this as a version of Hilbert's Syzygy theorem, where instead of fixing the number of variables of the polynomials, we're fixing the number of polynomials and their degrees. I thought I heard something. No. No question? All right. All right. So the next thing I'll do is try to explain a bit about the proof of this conjecture, Inanion and Hockster's proof. And for this, I need a definition that they came up with, which is surprisingly powerful. So the definition is the strength of a polynomial. So what the strength of a polynomial is you want to take your homogeneous polynomial f, and you want to decompose it as a sum of lower degree things. So I want both the g's and the h's to be positive degree because I want to avoid trivial decompositions. Then the strength is you take your f, you decompose it as a sum of lower degree things, and you choose the minimal s such that you can do that. All right, so as an example, the strength of this quadric down here, I claim is 2, and it's visibly at most 2. Because I've decomposed it, this is linear times linear plus linear times linear plus linear times linear. So it's kind of demonstrably at most 2, and then there's an exercise to check that it's actually, you can't do it with strength 1. So that's one example to get a sense of what strength means. Another example is strength 0 is equivalent to being reducible. If you're strength 0, then you factor as the product of 2 lower degree things. So strength 0 means reducible. Strength infinity is only possible if you're a linear form. And if you're a linear form, I mean, you can't, there's no way to do it with lower degree things. But if you're not a linear form, then you can always write your polynomial as x1 times something plus x2 times something plus blah, 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 plus xn times something, right? And so any polynomial has strength at most n minus 1, I guess. Any polynomial of degree at least 2 has bounded strength. The strength is bounded by the number of variables. And so that's what I'm trying to get at in this comment here. I'm saying this notion of strength, it can only go to infinity if the number of variables go to infinity. So it's correlated to the number of variables in some subtle way. But we don't want to, we're not referencing the number of variables. One other notion I will need is the kind of notion of strength of a set of polynomials. And for that, I'm just gonna take the minimal strength of a k-linear combination of those elements. It's really essential we take k-linear combinations. If we allowed, s-linear combinations, we'd always have strength 0 because you could just take f1 and multiply it by x1. So the kind of only reasonable notion is to do something that involves k-linear combinations. So that'll be what we mean by collective strength. All right, let me pause for questions. This is a key definition. I want to see if there are other questions on it. Yeah.
Can you actually compute the strength of a polynomial?
No. So I had this at the very end. Justin Chen, actually, at one of these Macaulay 2 workshops, tried to write some code to do it, and it is brutally slow. So if you think about strength, the strength of a polynomial is essentially a secant variety computation, right? You think about when you're decomposing as a sum of these lower degree things, it's like if I have a cubic and I'm decomposing as linear times quadrics, you would take the space of reducible cubics, linear times quadrics, and that's a subvariety in the space of cubics, and then the secant varieties of that would be the strength, or I guess the border strength, 1, 2, 3, etc. loci. So that's the best we know to do. I don't know of anything better. You can relate strength to the codimension of the singular locus, so you can get a bound in one direction, but it's generally not sharp. And so no, and I would love it if someone could do that better. And I genuinely don't have good ideas about how to do it, David. Other questions? So I will note, two of my students, Maya Banks and Juliet Bruce, in ongoing work, they've been investigating this. Oh yeah, go ahead with the question, please.
There are actually two questions. So
Yeah.
One of them is whether the concept of strength was studied for more general case, just a graded ring.
Great question. But this is a great question. Okay. So I believe the concept of strength, well, it actually has a long history, strangely. So it came up in Inanion Hockster's work, and they defined it there. And that was the first place I ever saw it. But then it turns out it appears in some other contexts. So in arithmetic geometry, some related notions have appeared when studying rational points on hypersurfaces defined over rational numbers. And things related to strength appear there. In the inhomogeneous case, what they do is they study the key invariant seems to be the strength of the top degree part of an inhomogeneous polynomial in the work that I've seen, shows up there. A related notion appears, I'm going to screw this up, slice rank. Slice rank is a related notion that appeared in the study of the cap set problem. And that had to do with these, strength. Polynomials are symmetric tensors, right? But you could study arbitrary tensors. And in that context, this notion of slice rank appeared, and it bears a really close connection to the notion of strength. So it appeared in these other contexts as well. And yeah, I think it remains very much in flux. But I was unaware that it had appeared in this arithmetic geometry stuff until something like 6 months ago or something. We kind of stumbled across it. So, yeah. Did that answer the question, Irena?
I guess so. There is another related question.
Yeah.
How is strength related to tensor rank?
How is strength related to tensor rank? So, let me think. So if you think about SIMD, a polynomial as a special, as a symmetric degree, a symmetric D tensor, then tensor rank would be decomposing it as a sum of essentially pure products of linear things, whereas strength allows you to decompose it into arbitrary degrees. So linear times degree D minus 1 instead of just pure linear things. So it's a more flexible notion. It's generally going to be smaller than something like tensor rank or Waring rank. It'll generally be much, much smaller. Yeah.
Another question along the secant.
Great question. Yeah, go for it.
Direction. If the secant locus contains the tangent locus too. It's not exactly secants. It's lines joining 2 points on the two different varieties, right? The cubics and the quadrics in your example. But if you're looking to decompose it into products of two quadrics, and you look at secants, then don't you have trouble with when it's on a tangent line instead of a secant line?
Probably. I mean, I'd have to think a second.
More like border.
It's more like border, you know, so there's a border rank, there's a border strength versus strength concern. So strength is not obviously Zariski closed, the same way tensor rank is not. You'd want to talk about border strength and something like that. Yeah. And this is something that I think remains pretty poorly understood, but a couple of my students, Banks and Bruce, are thinking about related things. But there's a lot of open questions there about, you know, yeah, trying to understand strength versus border strength in analog with those who know what I'm talking about with tensor rank in comparison with border tensor rank. Other questions? These, I'm in.
I think this is it for now.
Okay.
There are actually two other questions if you scroll up, if you don't mind. So one of them was whether or not there's an explicit effective bound from the Inanion Hockster theorem, and the other one was about generalizing from ideals to modules.
Great. Let me come back to, so the explicit bound is, last I checked, the answer is no, but these new results of Inanion Hockster don't, I mean, in some cases they do, but I think in general.
Daniel, could I interrupt?
Yeah, go for it.
Yeah, depends on what you mean by explicit.
Yeah.
Right. It's an explicit, all the bounds are explicit recursive, but for quadrics, there really is an explicit bound. For cubics, it's n-fold exponential. For quartics, it's completely out of the universe. And even worse for higher degree. In some sense explicit, but not in any sense you can write down.
Yeah, perfect. Thank you, Mel. That's, yeah. I don't have anything to add there. And then for modules, there are bounds for modules. Let me, maybe when we get a little further, I can mention those results. All right. So I will note, by the way, that
Actually, can I interrupt one more question?
Yeah, go for it.
This result about quartics and 100 variables, is this, why do you mention 100, and is there some more general statement here?
Yeah. So I was just trying to give a sense that yeah. So the reason I mentioned it is it's not clear what the maximal possible strength even is. We have some notions. So it's known, you know, for if you want to decompose solely in terms of linear forms, say the GIs are linear and the HI are degree d-1, then that would amount to essentially, over an algebraically closed field, let's say, that would amount to essentially what are the linear spaces that live inside of your hypersurface? And there's been a lot of studies on that. And so, you know, it's kind of known that the size of the linear space, the size of the largest linear space inside of a general hypersurface of some degree grows as the number of variables grow. And so, you know, for instance, if you look at 100 variables and you look at quartics, any general quartic will contain a P9, and that can give you a bound of 90. But then there's a question, which is the best way to find kind of these decompositions to compose it as linear times degree d-1, or are you better off mix and matching with, say, some linear times d-1, some quadrics times d-2, and so on and so forth. So Banks and Bruce were looking at quartics and quintics and essentially proving, I'm not sure, you know, the state of affairs, but their conjecture, possibly even theorem at this stage, is that linear decompositions are the best. So for general things, the strength will always be realized by a composite decomposition involving linear and d-1. And so that's all. But more, there are just a lot of mysteries about how this behaves in various cases. Did that answer your question, Stephen?
Yeah, I guess I was just wondering how general this example is. I mean, is it like, do you have some idea of how strength is supposed to grow in relation to the number of variables, or? Yeah,
so based on what's known about linear spaces inside of hypersurfaces, I don't think I can do it off the top of my head, but I think it's like if you fix D and you let n go to infinity, you'll get a linear space of size root n, I think root n inside of it. Or maybe it's n to the 1 over d, I forget, but it's some fractional exponent of n. So the linear spaces will grow, and that means the strength will kind of get further and further away. The maximal strength will get further and further away from the number of variables. So I mentioned on this slide that the strength is always bounded by the number of variables, but in fact, if n is very large, the maximal strength will never be that high. At 100 variables, the gap is about 10. At 1,000 variables, the highest strength would be, I don't know, I can't do it off the top of my head, but 980 or something. You'll kind of see a gap in that way. And that's all based on these classical algebraic geometry results about linear spaces inside of general hypersurfaces. And so that gives an upper bound on the strength. And so what Banks and Bruce have done is in degrees 4 and 5 are trying to show that the known upper bounds are actually sharp, that in those cases you can't do better.
There is one more question, whether in this case strength is actually Zariski closed.
In this case, strength is actually Zariski closed. I do not know. So I mean, the strength 90 locus, strength at most 90 locus would be the whole thing. But I do not know if strength is Zariski closed outside of quadrics. In quadrics, it happens to be because it lines up with rank in a sense. I don't know, Stephen, do you know, are there, even for cubics, I don't think.
Oh, I think the question is just, in this specific example, is strength at most 89 then Zariski closed?
Oh, I don't know. Yeah. Yeah, I don't know. All right. So let me move on. Let me see. We're supposed to take a break in 5 minutes, right? So.
Then not really. I think we take a break when you like it.
Okay. Okay. Well, I'll do it. Thank you, Irina. Okay. So let me say the idea that for me at least captures, or one of the key ideas in the proof of Stillman's conjecture is something we'll call the Inanion-Hockster principle. And I want to spend a bit of time on this slide as well. So the idea is that if you have polynomials of high collective strength, then they should behave approximately like independent variables. And I'm going to call this a principle because it's it's a vague, non-rigorous statement. But the idea is it's a way to make predictions for theorems about polynomials of high strength. So you start with a fact about linear forms. Like if you have R linear forms, they make a regular sequence. Or sorry, R variables, excuse me. They form a regular sequence. And then the idea is that the principle predicts a statement, which would be that R polynomials of high enough strength, high enough collective strength, would also form a regular sequence. If the strength is high enough, they will inherit the property on the left-hand side. And then, of course, the predicted statement is a mathematical statement, which could be true or false. And in the case I've demonstrated here, the predictive statement is true. It's a theorem of Inanion-Hockster's. And as we'll see, it's kind of the essential theorem underlying their proof of Stillman's conjecture. And so this is what we call a principle. And the reason we highlight it many of the results in the Inanion-Hockster paper can be understood in this context. So x1 through xr form a prime ideal. And so you might predict that any polynomials of high enough strength will define a prime ideal as well. And it turns out that that's a theorem. And that theorem is another one of the major theorems in Inanion-Hockster's paper. X1 through XR will define a variety which is smooth in high codimension. And so you might predict that any polynomials, F1 through FR of high enough strength, would define a variety that is smooth in high codimension. And that turns out to be a theorem, and it's another one of the major theorems in Inanion-Hockster's paper. so this was a way, this principle was meant to capture many of the essence behind many of the results in that work, and provide a simple way to think about it. Where was I going? I forgot to say early on, I was agnostic about my field at the beginning, and for some of the results you need algebraically closed, or at least a perfect field. So I don't want to get into the weeds there, but some of the results that'll come up, you need that on. All right, let me pause for questions on this one.
There is a question, what is collective strength?
Yes, so remember, collective strength it's the minimal strength of a k-linear combination. So it's a way to assign strength to a set instead of to a single element. And we want to allow combinations, but just k-linear combinations. So it's almost like the minimal strength of the element in the list, but you allow this kind of change of basis possibility, homogeneous changes of basis.
Okay, there are no other questions now.
Great. All right. So before we go to the proof, I want to note that oh no, there's a typo. That there are a number of results in the spirit of this principle that I came across. We've come across since Inanion Hockster's paper. So the idea is that if the collective strength of your polynomials is sufficiently large, then you get many instances of this principle. Many properties of independent variables pass to ideals of polynomials of high strength. So we've already said they form a regular sequence. Polynomials of high strength form a regular sequence. This was mentioned on the previous slide. The variety defined by polynomials of high strength is smooth and in high codimension in an explicit sort of way. That appears in Inanion Hockster's paper and in a different format in work of Kasd and Ziegler. I mean, if you look at the vanishing of linear forms, that's a linear space. And those spaces will have trivial Picard and Chow groups. And it turns out that the same thing is true for the vanishing of a set of polynomials of high enough strength. That's the work of a number of different authors. There are even some interesting geometric consequences. So just looking at a polynomial in one polynomial, the vanishing of a polynomial of high enough strength will be unirational. This follows from work of Harris, Mazur, Panduri, Panda, and then follow-up work of Chen. And again, the vanishing of x1 is of course unirational. It's just a linear space. So I see this as kind of in the spirit of this principle. A property of v of x1 is passing to a hypersurface of high strength. And then the last one is for me the most mysterious. It comes from number theory. And it says that, I mean, if you look at the vanishing of x1, that's a linear space. It satisfies the Hasse principle. And the same thing is true for the vanishing of a polynomial of high enough strength. This is an old result of Birch. And then there are some other related results that have appeared in the interim. So there's this funny phenomena that I don't fully understand, which is that properties of sets of independent variables seem to be held by ideals of polynomials of high enough strength, and it transcends algebra. It goes into algebraic geometry and even into number theory. I have a couple caveats below, but that was a lot. So let me pause for questions. Any good ones? You raising your hand, Mel? No.
Well, there is a question whether it's okay to assume that K is perfect instead of being algebraically closed.
Yeah, so let me see. For unirational, it gets scary because what unirational means. So the results, the number 3 and 4 I'm citing both assume algebraically closed. For the regular sequence, perfect is fine. And for 1 and 2, perfect is fine. Yeah. And you might even be able to go further. I don't remember. Yeah.
So there is a question, does it mean that the concept had been already defined?
No, well, in the work of Schmidt, following up on work of Birch, had come up with the same definition of strength independently, somewhat remarkably. But no, some of it is using Inanion Hockster's results to recast results in the literature. So what Harris, Mazur, Ponderi, this is a great question. What Harris, Mazur, Ponderi, Panda actually prove is if you have a hypersurface, a smooth hypersurface of degree D in n variables, and n is super large relative to D, then you're unirational. Wait, someone interrupt me. No, okay. And the point is the Harris, Mazur, Ponderi, Panda theorem can be understood in terms of strength via Inanion Hockster's result in number 2. So the fact that strength and high codimension are interwoven lets you take results about arbitrary smooth hypersurfaces and turn them into results about high strength polynomials. So a number of the results I'm citing are phrased in terms of the locus of the codimension of the singular locus, but Inanion Hockster showed in number 2 mentioned here there's an equivalence with strength. So yeah, so for the most part, no, but kind of in retrospect, this phenomena you can see in various places.
Next question, what does smooth in high codimension mean?
Okay, so what I mean is you've got a variety, and I mean, you look at the codimension of the singular locus. So I want that to be really, really big. So like if you're smooth, then that's good. But if you're like a billion dimensional variety that has one singularity, that would be smooth in codimension. I don't know, it's a really big number.
Okay, one more question. How large is sufficiently large? Something in terms of R and D or?
Yeah, it's always in terms of R and D. So sufficiently large is in terms of R and D. As Mel mentioned, some of these are explicit, can be made explicit in a sense. Some of the ones down at the bottom can be made explicit in a very precise sense. So 3, 4, and 5 have very explicit bounds, that aren't horrible. Yeah. Let me just see, before I'll take more questions, I'll note.
Could I comment?
Yeah, go for it.
So that function is linear in the number of forms for quadrics and quadratic for cubics, but the bound we have for quartics is much, much worse, although you can write it down.
Yeah.
But it's possible that there's a much better bound. So it might just be what you might conjecture from quadrics and cubics as far as we know.
Yeah. Thanks, Mel. Yeah, it'd be really interesting to I think understand that better.
And Daniel, could I ask a quick question also?
Go for it.
When you say it's explicit in number 3, so their theorem, though, it's already assuming they're a regular sequence. I mean,
oh, you're right. I'm totally wrong. You're right. I totally blew that.
So
yeah. All those theorems assume it's a regular sequence.
Right. I mean, 3, 4, and 5 are really theorems about regular sequences, and you're using
that's right.
Hockster and okay. I just wanted to be.
That's absolutely right. That's absolutely right, Chris. That was misleading. Thank you. Yes. Okay. Just quickly. I mean, it's worth noting not everything about the linear forms is going to be inherited by high strength polynomials. So to give a kind of dumb example, if you mod out by linear forms, you get a regular ring. But if you mod out by polynomials of degree at least 2, you never get a regular ring. There's always, it's never a regular ring. So So there's this question, which is to basically, can we sharpen this principle? Can we better understand which properties should fall into this and which can't? And I think it's a really interesting question. I'm kind of surprised to see arithmetic properties appear in this list. I would not have expected that when I first thought about these things. All right. So let me see. Now is maybe a good time to take a break because when we come back, we're going to get into a proof. I'm going to start talking through the proof and then moving on from there. So yeah, take a break. So I'm going to try to sketch the proof and how this principle, this idea about high strength polynomials having nice properties is connected to Stillman's conjecture. So first, I'm going to note a lemma, which is just that if you have your ideal, and here I'm going to let, to emphasize the lack of dependence on the number of variables, I'll let my ideal be in the polynomial ring with countably many variables. The argument is if the generators of I belong to a subalgebra generated by a regular sequence, then the projective dimension of the ideal is bounded by the length of that regular sequence. And the statement is clever because it provides a new way to bound projective dimension, but the proof is actually fairly elementary once you've seen the statement. So the proof is you take a polynomial ring in T variables and you map it to S by sending the ith guy to G sub I. That's a faithfully flat map since the G's formed a regular sequence. Then the generators of I lived in the subalgebra. And so you can find an ideal in R, which pushes forward to give you I. And what you do is, for each generator, you write it as a polynomial combinations of the G, and then you replace the G's by the Z's, and that gives you your ideal J. And then by flatness, the projective dimension of the ideal in R is the same as the projective dimension of its push forward, and that's I. So since ideals in R can have projective dimension at most T by Hilbert-Syzygy theorem, that tells you that the projective dimension of anything that was pushed forward in that way also has projective dimension at most T. So it lets us bound the projective dimension by trying to realize I in a subalgebra generated by a regular sequence. So that's the first one. And then this allows for a sort of induction. So this combined with this high strength properties will let us do an induction. So let me try to sketch the induction. I know it's a busy slide. It was hard to get this right. Let me try to sketch it in the case of 4 cubic polynomials. So the idea is going to be at each step, we're either going to have a regular sequence or we're going to have somebody of low strength, and we're going to iterate on that. So if the collective strength of my original guys is big enough, then they're a regular sequence and the projective dimension is at most 4. If the collective strength is not big enough, then we can rewrite up to a change of coordinates. We can rewrite one of those generators in terms of lower degree things. So then what we've done is we've moved from the situation of 4 cubics to the situation of 3 cubics and a bunch of linear and quadratic things. And and a bound, but the linear and quadratic things, there's a uniform bound on the linear and quadratic things that only depends on the numerical data above. And so now if at this stage we're a regular sequence, then our projective dimension is at most 2, it should be a capital N plus 5. It's at most the number of guys, because F1, F2, F3, F4 is in the subalgebra generated by these, because F4 is demonstrably in the algebra generated by the G's and H's. So if these new guys are a regular sequence, then we win by the lemma on the previous page. We get a bound on the projective dimension. If they're not a regular sequence, well, then we can blow one of the things up into lower degree forms. So maybe the F3 up to change of coordinates, we split into lower degree things. And then again, if the new guys, the new F, G's, H's, G primes, H primes, and so on, if those are a regular sequence, we get a bound on projective dimension. If not, we split one of the guys into lower degree things. And so we get this iteration of cases where at each step, we terminate if you're a regular sequence, or if you're not a regular sequence, that means something had low strength. So we can split one of your objects into a bounded number of lower degree things. And if you give the right kind of term order on the degree, on whatever, if you analyze this in the right way, you can see the process has to terminate. Sooner or later, sooner or later, the process has to terminate. And so there's only a finite number of branches that this process could have at any stage. So the crux of the idea is this theorem that high strength polynomials are a regular sequence, and therefore if you're not a regular sequence, you can split one of your elements into a bounded number of lower degree things. And that argument actually produces something stronger than Stillman's conjecture. It produces the existence of small subalgebras. So what it says is that if you have an ideal generated, or one version of it, if you have an ideal generated by a bounded number of polynomials of bounded degree, then you can find a number S, which only depends on R and D. It doesn't depend on N, such that I lives in a subalgebra generated by a regular sequence of length at most S. So said another way, it means that I can be realized as via flat descent by an ideal defined in a polynomial ring in S variables. And so in essence, I comes from, via flat descent, a polynomial ring in S variables. And so anything which is stable under flat maps, like projective dimension or the Betty table, things like this, will be preserved under that passage. And so this kind of explicitly connects Stillman's conjecture to Hilbert's Syzygy theorem. It says Hilbert's Syzygy theorem for a polynomial rings in S variable transfers via this flat descent and this subalgebra theorem to any ideal generated by R polynomials of degree at most D. So the theorem, this subalgebra theorem is stronger than Stillman's conjecture. It yields many more boundedness results because again, you have this connection between ideals and R polynomials of degree at most D and this other polynomial ring with at most S variables. So you can kind of descend finiteness results. You can use the classical Hilbert results on the polynomial ring in S variables and descend those to facts about ideals generated by a bounded number of polynomials of bounded degree. So just as an example, if you want to see this, if you have two quadrics, there's basically two cases. If they're a regular sequence, well, then they're in the subalgebra generated by themselves. If they're not a regular sequence, then they have a linear form in common. So they're L1, L2, and L1, L3 with the Li's linear, and then they live in the subalgebra generated by those linear forms. So there's kind of only two cases. And more generally, any ideal of most R polynomials of degree at most R will branch into essentially a finite number of cases similar to this example. That's what the argument on the previous slide is showing. All right, let me pause for questions because we've completed the proof of Stillman's conjecture. I mean, modulo a lot of details, but modulo a huge number of details. Yeah, questions?
I don't see any questions at this point.
All right. So again, I just want to emphasize before I flip the slide, which is that this small subalgebra theorem really is earlier I said Stillman's conjecture was like a version of Hilbert's Syzygy theorem as n went to infinity, and this small subalgebra theorem explicitly connects the two. It shows how that the bound, the proof of Stillman's conjecture is leveraging Hilbert's Syzygy theorem for a polynomial ring in S variables. and it's using it in this way. All right. So what I want to do next is turn to something that Stephen and Andrew and I got interested in, which is, well, what happens to the Inanion-Hockster principle as n goes to infinity? And I've kind of highlighted what I'll call the limit Inanion-Hockster principle. So earlier, the Inanion-Hockster principle said, if polynomials have high collective strength, then they should behave approximately like independent variables. And so the limit of large is going to be infinity, and the limit of approximately is going to be exactly. So I claim this should be the limit of the Inanion-Hockster principle as the strength goes to infinity, or as the number of variables goes to infinity. And now to make sense out of this, I'm going to introduce a ring where new elements of infinite collective strength exist. So remember, for polynomials, for the polynomial ring, the only elements of infinite strength were linear forms to begin with. So for this to be interesting, we need a new framework. And I'm going to start with the concrete one. So I'll define this funny looking ring to be the graded ring where the degree d elements are arbitrary combinations of monomials in the xi. So I think this is best understood by an example. Sum xi squared for I equals 1 to infinity is allowed. We allow wide power series, but all the terms need to have the same degree. So this is an inverse limit of polynomial rings where you surject onto the system is you kill the last variable, and then you take the inverse limit in the category of graded rings. So it's an inverse limit of polynomial rings in an appropriate sense. It contains new elements of infinite strength. So if we're in characteristic not equals 2, it turns out that the sum of xi squared has infinite strength. That's an infinite strength polynomial. There is no way to write that as a finite combination of elements of lower degree. At first glance, it appears really bad. It's very non-Noetherian. So in degree 1, it's the basic, it's a direct product in degree 1. The vector space in degree 1 is a direct product over the xi, and so it has an uncountable basis even in degree 1. It appeared in one place previously I'd seen it appeared in work of Snellman, who studied universal Grosvenor bases and had used this to try to analyze some of that. So there was some connection here. All right. And so I want to use this ring to make sense of this limit Inanion-Hockster principle. And actually, you know what? I should pause. This is a weird ring. People haven't seen it before. Let me pause for questions. Any questions? So it's like power series, but you let them go to the side instead of up, All right. All right.
No questions.
No questions. Great. So then the theorem is that this funny ring is actually a polynomial ring. Even though it's this horrible non-Noetherian thing, it's actually as simple as you could possibly hope for. So it's isomorphic to a polynomial ring K adjoin a set of variables where the set of variables, where Z is a maximal set of infinite collective strength. And if you want to get into the details, Z will contain uncountably many elements of degree D for each D at least 1. So it's a lot of variables, but it's isomorphic as a graded ring to K adjoin just a bunch of variables. So it's kind of as simple as could possibly be. So let me try to make sense out of this. So first, as an example, to first get your head around it, maybe we can think about the power sums. So the sum xi to the d in characteristic 0, I should have said. Those, each of those elements has strength infinity. And so taken together, they have collective strength infinity. And so those could be chosen to be a subset of this set Z. They should act like independent variables. And that's actually known in combinatorics, where they study the ring of symmetric functions, it's known that these power sums, these infinite power sums, are algebraically independent. So it's kind of our theorem. I mean, that is an example of what you might think for this theorem. Although the theorem is very much the limit Inanion-Hockster principle. I mean, it says, this set Z is a set of infinite collective strength, and it says, any subset of it can be realized literally as independent variables in this limit ring. So elements of infinite strength are acting like independent variables. So in particular, elements of infinite strength will inherit all sorts of nice properties because independent variables have all sorts of nice properties. So this provides new possibilities for proving Stillman's conjecture. I'm not going to go too deep into those because we already saw a very nice sketch of a proof of Stillman's conjecture. But it provided a new angle on, there's a couple different ways to do it. I might do one of them later. It also, it allows, it gives a framework for studying universal Grosvenor bases. So this was appearing in work of Dreisma, Lassan, and Lakin, where you could study, polynomials like the sum Cij xi xj for all ij. So that would be like a universal quadric, and you could try to analyze Grosvenor bases in that context. And having nice finiteness properties like the corollary at the bottom enable you to actually make reasonable arguments in that setting. But the main point I want to get at is that this sort of theorem is exactly codifying the limit of the Inanion-Hockster principle. It's saying that infinite strength polynomials are independent variables. All right, so let me pause a second, see if there were questions I missed before I flip.
Not really. There were some questions, but Steve answered it, so.
Okay, great.
Okay.
Thank you, Stephen. All right. So I was going to do the proof. Maybe I'll just mention it really quickly. Just sketch it. I mean, the idea behind the proof is that, well, choosing a maximal, this set Z was a maximal set of infinite collective strength. That's equivalent to choosing algebra generators, because finite strength is equivalent to being in the maximal ideal squared. It means that you can decompose as a combination of other things. So we naturally get from this set Z, we naturally get a surjection, and we want to prove that it's an isomorphism. And the argument is basically assume it's not, choose a kernel element of lowest degree, and then take a derivative. You know, that this funky ring still has partial derivatives like d dxi, and if you kind of write out your relation in the right way and you take a derivative in the right way, you can get a new non-trivial relation of lower degree, and so you can descend in that way. I won't go into it in too much more detail than that, I guess, just for time, and also because I'm not sure it's worth getting into the details. Of course, what I just said, you know, when you start talking about derivatives of things, that works a little better in characteristic 0 than in characteristic P. So in characteristic P, the proof is harder, and there we use these Hasse derivatives, which are like divided power operators or something. But the essential idea is you have this simple you define this natural surjection, and then if it's not, you know, if there were anything in the kernel, you could produce something of lower degree. All right, so skip over the proof. That's enough on the proof. All right, so I knew I would be running into time issues, so I did this one a little short. I'll say this inverse limit polynomial ring, this funny power series guy, is one way to talk about the limit of polynomial rings as the number of variables goes to infinity. There's another way, which actually has much nicer properties in some sense. And that's to use the theory of ultra filters and ultra products. So I'm not going to go through those definitions. knew time would be an issue here. But if you know what an ultra power is, it's this construction, an ultra product. It's a construction that's based on ultra filters, this thing that comes from, I think it's coming from logic in a sense. They aren't actually that complicated. It probably takes, a couple hours to learn it, but a first-year grad student could easily spend some time on Wikipedia and teach themselves about ultra filters and ultra products. But broadly, it's a way to take an element of the ultra product of rings is going to correspond to a collection of degree D polynomials, but then there's a funny equivalence relation on it. So it's not the direct product. It's like the direct product over a bunch of polynomial rings, but with this complicated equivalence relation on it. But the ultra product, it provides a way to kind of patch together a bunch of degree D polynomials and get a single element. And the theorem we have about the inverse limit ring, this power series ring, is also true for the ultra product ring. So this ring is also a polynomial ring. And here the variables correspond to sequences of polynomials where the strength is unbounded. So it's the infinite strength elements in this ultra product ring correspond to these collections of polynomials of degree D where the strength is getting larger and larger. And the advantage of this framework is it just makes it easier to pass properties from the infinite strength to the finite strength level. So maybe here it's worth noting something, which is I talked about this limit Inanion-Hockster principle, but if you want to actually get instances of the Inanion-Hockster principle, you would want them not for the infinite strength elements in these crazy limit rings, you would want them for collections of actual polynomials in an actual number of variables. So you want to be able to take a property that was true for infinite strength elements and say it's also true for polynomials of high enough strength. So kind of pass down. And that kind of top-down approach works very well using this ultra product machinery. And in some sense, I think that gets at the difference. So one corollary of this theorem is this instance of the Inanion-Hockster principle we saw earlier, that high-strength polynomials form a regular sequence. And in Inanion-Hockster's work, they somehow build up nicer and nicer properties of high-strength polynomials and use that inductively to get their result, whereas we try to go in the opposite direction. We prove instantly you have these nice properties for infinite strength elements, and then we try to descend it to high strength collections. All right, questions on ultra product ring?
Well, there is a question about Z. Is there a nice Z with an intuitive description? Is there also a sequence description of a choice Z?
No, definitely not. I mean, even in degree 1, you're talking about choosing a basis for over a direct product, right? So there, I don't think there's any natural best choice. But when you get into higher degree, just no, because no, I mean, I think it would be hopeless. I think it's existential. There's no reasonable explicit description. Stephen, you would agree with that, right?
Yeah, I think you have to use the axiom of choice. So, I mean, it sort of says you probably can't write anything down explicitly.
All right. So let me see. I've got, should I stop in 6 minutes or so, 7 minutes? Do I have that right, or was I supposed to?
Yeah, it's roughly about that, but you can go a little longer.
Yeah, I mean, I don't want to go over.
Yeah.
All right. So let me say I'm going to change directions for a minute and give more of a sketch here, but talk about another direction that's related that I think is really interesting, which is Stillman's conjecture was like our Syzygy theorem as n goes to infinity. So what about the Hilbert basis theorem as n goes to infinity? So of course, the Hilbert basis theorem fails for infinite affine space. There are, and I'm going to mention this topological one, which is we'll study descending changes of Zariski closed subsets instead of ideals. But even that fails for infinite affine space. But But it turns out something similar is true if you look at infinite dimensional affine spaces which have appropriate large group actions. So I put two examples up here, and I'll kind of do them. Yeah, let's do them. So the first one is my space is going to be just spec of a polynomial ring and a countable number of variables. But I want to think of the points of that space as corresponding to degree 1 polynomials in this wonky limit ring via the correspondence. The CIs become the coefficients of that polynomial. And if you think of it in that way, then x1 inherits a GL infinity action, which is the GL infinity action on this funny ring. And then it turns out that any descending chain of GL infinity Zariski closed subsets of x1 will stabilize. So if instead of looking at arbitrary Zariski closed subsets, you look at ones that are invariant under the group action, you recover a sort of Noetherianity. And in the case in this case, it's kind of for silly reasons, which is that there are only two GL invariant closed subsets of this space. There's the whole space in the origin. But if you pass to the next example, if you start looking at quadrics, the same thing is true, except here it's less trivial. There are lots of GL infinity invariant closed subsets. They're the loci of bounded rank. And any descending chain will terminate, because any descending chain starts with rank at most like 10 billion. And then when you descend, the rank loci have to go down, and so eventually it'll stabilize. So here you can get, in this other case, you can get chains of arbitrary length, but any chain will eventually stabilize, any chain of invariant closed subsets. And so this suggested a sort of Noetherianity result for spaces like this. So I believe it was Sam and Snowden, I meant to confirm this, who were asking at some point whether these sorts of results held in a much more general setting. And Jan Drijsma proved that it did. So for the purposes of this talk, we'll just look at the cases where you look at XD is basically the space of degree D elements in this wild ring. And I'll look at R copies of it. So a point of XDR is like R elements of degree D in this ring. And Drijsma proved that this is GL infinity Noetherian, which is to say, in that space XRD, any descending chains of GL invariant closed subsets will stabilize. And I felt the need to add a technical footnote, which is for something much more general. It applies to wedge products and Schur functors and sums of them and so on. But I didn't think we needed that for this talk. But these kind of parameter spaces satisfy this GL infinity Noetherianity. This Drijsma's result was part of a much broader literature that kind of abuts to the things I've been talking about, that studies S infinity actions and Noetherianity with respect to that gets into the theory of FI modules, the theory of twisted commutative algebras, as well as more precise results in special cases like quadrics and cubics. So there's just a ton of work in this direction, and I don't have time to get into. But the reason I wanted to mention this is because it provides another viewpoint on Stillman's conjecture. So the idea is, oops, I have my XDR is wrong, but the idea is, if you think of XDR as this parameter space for R elements of degree D in this funny ring, you can write down universal polynomials. So these CI alphas are just arbitrary variables, but and the X alpha is meant to be a monomial of degree D. And you can write down a set of universal polynomials, F1 through FR, where you've just put variables in for the coefficients. And so then you have this universal family of collections of R polynomials of degree D, and it lives over this space XDR, which satisfies this funky Noetherianity property. And so this opens the door to a sort of generic flatness proof of Stillman's conjecture, which I'll mention vaguely here. The details are actually quite hairy, but I'll kind of mention the big idea, which is by our result on these funny inverse limit rings over the generic point, you're looking at a polynomial ring. And so you can study for your universal family, you can study its free resolution, and it'll be finite because over the generic point, it's a polynomial ring. And you can leverage that to get a sort of generic flatness for this universal family. And then you can use that to start building a flattening stratification. So taking this universal family and breaking up the base into strata, where over each strata, the family is flat. And then since flatness will be unaffected by the GL infinity change of coordinates, you can assume the strata are GL equivariant. And then Dreisma's result tells us that, in fact, this universal family therefore has a finite stratification. And this gives a kind of alternate way to leverage a sort of, in this case, this generalized Hilbert basis theorem to get bounds on things like Stillman's conjecture or related things. All right. So this is where I'll stop, and I'll maybe stop here and turn for questions. So thank you, everyone.
Before we get into questions, I wanted to announce that there will be a tea room available for the half hour after this seminar, and I invite anyone who wants to hang around and chat to do so. If there are a lot of people, we'll divide into breakout rooms, but if there aren't too many, then we can all chat together. And now that Daniel has left, maybe we can ask him questions.
No, sorry.
There he is again. Any questions?
This is not a question, but I think somebody asked earlier whether, if you look at the polynomials of a given degree, whether the ones of strength at most k, whether that set is a risky closed.
Yeah.
And that is true over an algebraically closed field. And it's in my second paper with Tigran, Inanion, one that's in the transactions.
Oh, nice. I didn't know that. Thanks, Mel.
Okay, I don't see any questions. Several people said thank you.
Oh, yeah,
So thanks, Dan, for a wonderful talk.
Yeah, thank you all. Thank you all for coming.
Thank you. Beautiful talk. Thank you.
Yeah, thank you for coming.
Thank you very much, Dan.